Hello everyone, I'll be presenting this talk on behalf of my colleague Fariha. This is the outline of my talk. I shall begin with some of the light angle sensor applications we have in today's world. Then we shall move forward to some of the implementations of these light angle sensors. I shall explain to you guys what exactly a Shack-Hartmann wavefront sensor is and how it's different from the traditional light angle sensors. Then I shall move on to our device microfabrication, assembly, experimental data, and a brief summary. In today's world, there are many applications which might require you to know the angle of the incoming light rays. For example, in a solar power plant, these light angle sensors might be required to track, the movement of the sun to maximize the power output. Such sensors are also used for, for light gesture detection in laptops and other industrial machinery. Generally speaking, these light angle sensors are used for air surveillance and any application which might need location and tracking of devices which are reflective or bright in nature. Most of these sensors are actually present in nature and they're artificial as well. For example, many insects, they have the light angle sensors embedded in their system, in the biological system. For example, the butterfly, one of the types of butterfly, they have the sensors embedded in them, where what happens is they have a brief bearing image of the sun based on a calculated difference on the light intensity which falls on their eyes, and they calculate the difference in that, and that is how they kind of measure the bearing location of the sun. Fundamentally, what happens is when there is an opaque object in front of the eyes, that casts a shadow on the eyes itself, and the location of this shadow depends on the apparent incident light rays of the sun. Now we can extend this phenomena, this principle, to artificial light angle sensors. For example, the one as shown in the lower left corner. It's a pinhole 2D sun sensor, and as clearly shown, it consists of a CCD CCD sensor and a light mask on top. The light mask consists of a small pinhole, and how this works is when there are incoming rays, almost all the rays, they are not allowed to pass through except for one single ray, which goes through the pinhole and falls on the CCD array. So therefore, how it works is the position of the bright spot on the CCD array determines what the angle of incidence might be. Now, this concept is extended to 1D grid shadow direction sensors, gate shadow sensors, and tilted face photodiodes as well. Here comes the interesting part, a new technique of detecting what your angle of incidence of light rays may be. It's called the Shack-Hartmann wavefront sensor. Any typical Shack-Hartmann wavefront sensor will have a microlens array as shown there, and an image sensor kept in front of it, right at the focal length of the microlens array. So how it works is this: if you have an incident light which has a plane wavefront, the image formed on the CCD will be that of periodic bright spots. If the angle of incidence changes on the right, as you can see, what happens is these bright spots, they shift. It is this shift that is measured and calculated for each lenslet, and that is calculated and sampled to finally get the angle of incidence of the original wave. We are extending this principle and making it even simpler. We use just one microlens and a partial CCD sensor you can use, as shown as in the figure. The deflection of the bright spot can be, that is delta XC, is directly proportional to the product of the tangent of the angle of incidence and the focal length. Now, the advantage of the SHS sensors is that it uses all of the incoming light rays to form a signal, which is the main difference. Whereas the previous ones, as I showed, they use the shadow concept, which means is that in this case, I have a lot more electrical output, a lot more electrical photocurrent, which means I can even track in low light conditions, and also of objects which are not that reflective, not that bright in nature. This is our main construction of our device. We can replace the CCD array, which I mentioned a while back, as either a PSD, which is a position sensitive detector, or a quad cell, as long as the spot size of the final beam is smaller than either of them. The relative position, that is the XY coordinates of the spot size, can be found out using the currents, that is IA, IB, IC, and ID. They are the outputs of the four photodetectors or the photodiodes on the four corners. And the incident light unit vector can also be found by measuring the currents at the four corners of the four photodetectors. This is how the quad photodiode was fabricated. I'll give a brief fabrication flow. So we start off with a N-type silicon substrate and deposit 500 nanometers of LPCVD silicon nitride, which acts as a diffusion barrier layer. We photolithographically pattern it to etch out the doping axis layers. We then subject this sample to 2 hours of doping at 1050 degrees Celsius, boron doping, which gives an approximate diffusion length of about 3 microns. The same process is repeated, but this time we need to do an N-type doping. So we do that and as phosphorus sources for 45 minutes at 1050 degrees Celsius. Now, finally, all the nitride layer is stripped off, and we grow a thin layer of passivation oxide, silicon dioxide, about 200 nanometers or so. And the step is finally ended when we deposit 200 nanometers of aluminum by using of sputtering and pattern them to form the contact pads. On the right, we have the SEM of the finalized image of the finalized device. This is the micro optics assembly, as shown in the figure. We have a shadow mask, which is sort of a spacer. It's 287.5 microns thick, and it is kept on the orifice, or is kept on the sensor itself. It has orifices for the sensor and for the metal contacts for the bond pads. Now, the ball lens is the critical factor here. It's embedded on this shadow mask so that all the light can be focused to that small point I showed a while back. Now, the focal point or the spot size is directly proportional to how small this ball lens is. For our experiments, we got a range of spot size in the range of 250 to 500 nanometers. Our device was characterized in this simple experimental setup where we used a white LED, which had an intensity of 1.25 megawatts per centimeter square at a distance of about 2.5 centimeters. The LED was actually mounted on a rod, which was kept about 2.5 centimeters away from our light direction detector. The rod was then attached to the set of micromanipulators, which was moved in X and Y direction, and that is how we did our experiments. Each photodiode at the four corners of our quad cell was measured individually with the help of a digital multimeter, and all the experiments were done in a closed shell, in a closed box. This slide shows the response of the quad cell, or one of the photodiodes of the quad cell versus the LED position. Now we move the micromanipulator in the X and Y direction, giving rise to an angular position of theta and phi. As shown as in the left graph, or in the right as well, there is a certain peak at a certain angle which shows the maximum exposure of the photodiode to the incoming LED light. The same experiment was repeated but in this case, instead of using a simple white LED, what we used was that a UV laser. The laser had an intensity of 57 megawatts per centimeter square. So as it can be seen clearly that the trend is very similar, except the fact that the current output is much higher because the light source is much more intense. This slide shows the 3D response surface of a single photodiode current versus angle measured with the LED and the micromanipulator setup. The intensity actually drops as an angle makes the focal point land on adjacent PN junctions. It is also worth noting that the maximum intensity is not realized at normal incidence, but at a slightly inward angle that maximizes the intensity on one of the quad PN junction photodiodes. The dark red maroon area is where the plot indicates the highest photodiode current output. This slide shows the plots of the normalized X and Y positions of the spot based on the current which we got from the four different photodiodes, that is I1, I2, I3, and I4. And finally, we also measured the responsivity and noise equivalent power for our device. The circuit that we used, which shows in this slide, the op-amp is a TL084, and the detector and readout circuit display a responsivity of 0.32 ampere per watt and a noise equivalent power of 14 watt per square root of hertz. So in summary, we developed a 0.5 incident light direction sensor based on the Shack-Hartmann sensor principle. We made a device that utilizes a quad photodiode array and a ball lens that concentrates the light onto one spot projected on a quad sensor. The angular range was 15 degrees, at least more than 50 degrees in any direction, and the responsivity was 0.3 amperes per watt, and the NEP was more than 200 to the power 14 watt per square root of hertz. The calculations showed that the minimum signal which could be detected was approximately 2 picowatt, and the signal bandwidth was about 10 kilohertz. The light concentration by lens therefore showed that it can actually detect a lot lower power emitting from any of the dark objects as well. So that's it. Thank you.